Hello, everybody. It is the second talk on the Second ISC Winter School on Information Security and Cryptology. While the previous talk by Chester was on automation detection of differential fault and block ciphers mainly, in this talk, Maria is going to present effective attacks from ineffective faults. I would like to thank Maria again for accepting this invitation to present this talk, and I'm sure it will be very useful for the audiences. Maria Eichlseder is an assistant professor in cryptology, cryptography at Graz University of Technology. She could design ISCwsISC, a lightweight authenticated cipher that is among the winner of the CISR competition. Her research interests include the design and cryptanalysis of symmetric cryptographic algorithms, such as hash function and authenticated encryption algorithm, and also the underlying primitives. She is also interested in the robustness against misuse and implementation attacks, and a connection between cryptanalysis and physical attacks, such as fault attacks. She studied computer science and technical mathematics at Graz University of Technology and defended her PhD in 2018. Thank you again, Maria, and we are ready to hear your nice presentation.
Thanks a lot for the introduction and the kind invitation to speak here, Naso. So, as you already said, my talk is going to be about effective attacks from ineffective faults. What I mean by this is a technique that we developed a few years ago in Graz called Statistical Ineffective Fault Attacks. And what's great about this method is that it works even if the faults we can produce are not so reliable and if there are countermeasures implemented. And so what I want to talk about today is this attack and how to defend against it. And much of what I'm talking about is based on joint work with my great co-authors, which are listed here below. So Johann, Christoph, Hannes, Thomas, Stefan, Florian, and Robert. So let's have a look at the outline that I want to speak about today. I will first give another introduction to fault attacks. I know that you already heard about fault attacks in the previous talk, but I still want to recapitulate a bit and also put it in a slightly different vocabulary, which I find more suitable to present our own attack. So I'm going to look at the effect that we can produce with faults and how this is linked with differential cryptanalysis, the area that I usually work in. I will also recall some of the countermeasures that have been developed to protect against such fault attacks and see how different variants of fault attacks can defeat some of them, but usually not all. And this includes countermeasures against fault attacks as well as countermeasures against side channel attacks. And then finally, the main part of the talk is going to be about these statistical ineffective fault attacks that we developed. So I will first give an introduction how and why it works, so how you can apply it and what the reason is that it is so effective. And in particular, why it even works when there are many countermeasures in place, so even when the implementation is protected against side channel and fault attacks. And in the last part, I want to show a few directions how we can protect against this attack. So I first try to formulate a criterion when we can say an implementation is secure against this kind of attack. And then I want to introduce a countermeasure that we implemented with the co-authors I listed on the first slide. And some
Maria,
different...
Excuse me to interrupting you. I think we hear you with a little bit noises. Is it possible to cross-check your microphone once again?
Yeah, what sort of noise are you experiencing?
Yes.
What sort of noise?
Something like echo. Echo of your...
An echo. Okay. I can switch the microphone off and on. I can also try to switch to my Bluetooth microphone, but I think the sound quality is not so good. But wait a second, I can try that. And if this doesn't work, I can also try to connect with a different browser.
No, I don't prefer to switch to another browser because I cannot predict the consequences.
Okay. So does this also work with a noise? This is now a different microphone?
The same. The quality is the same.
The quality is the same. How about this? So I'm now switching through my microphones. Is this one better? Or also the same?
No, I think it's the same. I think it's fine. We can continue and...
So maybe somebody else is causing the echo, but then I should be hearing it too, and I don't really.
I think we can continue, and I will try to cross-check the microphone of the audiences. If there is anyone on, I will off the microphone.
Okay.
Thank you. Let's go. I can't hear you.
Can you hear me now?
Yeah, fine.
Okay. This seems to be very confusing. I can decrease my mic sound level. Yes, I can do that, of course. Is it better this way?
Wow, great.
Excellent. Okay. That was easier to fix than expected. Thanks for the hint, Siavash. Okay, let me know if there is anything else that I should tweak. Okay, so now let's have a first look at the different ways of how we can introduce a fault. You probably already heard some of the examples in the previous talks. And the nice thing is that there's quite a range of different methods how we can influence a computation that is ongoing and make it do something else than it should. So these include environmental factors, like, for example, very high temperatures, or also things that you can introduce intentionally, like tweaking the voltage or current of the power supply of your device. You can also try to manipulate things like the clock or the number of times that a particular operation is executed. So for example, you can try things like doing excessive memory accesses to a particular type or to a particular location in the RAM. And what you will likely experience then, due to effects like they are exploited in row hammer attacks, is that somewhere else some bits flip. You can also try wilder and more expensive things like radiation or shooting at your device with a laser. Now, what's nice is that most of these have very different effects on the computation. These can be effects that are long-term or that happen very suddenly, so a slow degradation or a very sudden effect. And we are particularly interested in this very sudden effects, which have been studied for a long time, originally in the context of testing what the effects of radiation are in nuclear testing. So these sudden effects can also come in two different shapes. They can be something that is permanent. So for example, if you have a circuit of your implementation and you destroy some of the wires there, or you short it, then you have a permanent damage to your circuit, and every time you execute it, it will make the same error. You can also cause temporary problems, which won't appear again the next execution. So for example, with the type of row hammer attack I mentioned previously, you will flip a bit in the memory one time, and this won't have any effect as soon as this value is overwritten again at a later point. So we are particularly interested in both of these, and both are relevant to what we can do. What we're interested in specifically is an error that we can reproduce several times. So either because we can repeatedly cause a temporary damage, or because we can produce a permanent error. And the sort of error also comes in different shapes. So the most typical thing we observe is that a data bit somewhere flips. So it switches from a 0 to a 1 or a 1 to a 0. However, we can also have more biased faults. For example, a fault that always resets a particular bit to 0, or at least does this with a certain probability. Or we can have things like skipping an instruction, which can have more complex effects depending on which instruction that was. And differential fault attacks, which you heard about previously, very often exploit the first kind of fault, where you flip a data bit. But in this work, we're more interested actually in less standard errors, so things that have a bias in a certain direction, and maybe also faults that don't cause exactly the same effect every time, because there is a certain noise where your fault setup is a bit complicated and you don't always achieve exactly the same effect. And what we're going to use these faults for is attacking symmetric cryptographic primitives, and specifically block ciphers. So in the following, we're always going to talk about this scenario where we have a block cipher here illustrated on the left-hand side. I'm not sure if you can see my mouse, where you feed in a message block and
yes,
a key. Sorry?
We can see your mouse, no worry.
Okay, okay. By the way, I also can't see your questions while presenting. So if there is a question, Naso, could you please alert me? Then I can have a look at the chat.
I will manage the question, and if there is any question from the audiences, I will let you know.
Great, thanks. Okay, after a number of operations, which you see here indicated by this cogwheels, we get some ciphertext. And we want to fault this computation, so introduce a computation error somewhere while it's running, and then we observe a faulty ciphertext. And in classical differential fault attacks, which I will get to in a moment, you receive both these outputs. So you do the same computation twice. You get once the output with an error and once the output as it should be. And more specifically, what this error does will depend on where the fault is introduced, because this block cipher comes in several rounds. And in one of these rounds, we need to introduce our error. And from that point on, our intermediate results will be incorrect. So let's have a look at a more specific example of a block cipher to settle the general vocabulary. I'm always going to be talking about substitution permutation network style block ciphers. These are block ciphers which have a simple round function that consists of 3 steps, some sort of key addition on top, then some sort of lookup table, which are S boxes, and then some sort of linear mixing layer where the outputs of the S boxes is transported to some different bit positions for the input to the next round. And what we usually do in differential fault attacks is we try to introduce an error somewhere near the end so that only a few S boxes are affected. We then obtain the correct and the faulty ciphertext, look at the difference that we have between those ciphertexts, so the XOR of the correct and the incorrect ciphertext block, and we can use this, we can then compute backwards and learn what the output of the last, in this example of the last faulty S box was. So to do this, we usually have to guess a part of the key. So in the toy example that we see here, we can, for example, guess a total of 4 key bits. So if you look at the last round key, K4, we can guess the 1st, the 5th, the, I guess it's the 9th, and the 13th bit position. And based on the linear layer we see here, if we guess these values of the key here, then we can derive from the ciphertext the output and input of the S box marked in red. And then if we use the inverse S box lookup table, we would get the intermediate result where this lightning bolt marks our fault location. And what we usually do is we guess this key candidate, compute backwards to this position, and then we verify whether the values we obtain match what we expect. What we would expect is, for example, if we know that we introduced a fault that flipped the bit of the first SBox input bit, then what we would expect from computing backwards is exactly this pattern. To receive two inputs at the SBox where the first bit is different because it was faulted, and the other bits are identical between the faulted and the original ciphertext. And if this is not the case, then our key candidate must have been wrong. If we do observe what we expected, this doesn't necessarily guarantee that we have the right key candidate for reasons I will get to in a moment, but it is a good indicator. If we do this, then we usually have several key candidates left, because some key candidates, even if they are wrong, might give us the correct result at the SBox input by accident. Now, one of the questions is, of course, how likely is it that we actually get the expected difference by accident, even though the key candidate was wrong? And to understand how often this happens, what I'd like to do is I would like to have a brief look at this differential fault attack from the perspective of cryptanalysis, specifically from the perspective of differential cryptanalysis, which is the area I usually work in. So this differential cryptanalysis technique was actually proposed by the same authors as differential fault attacks, but just a couple of years earlier, in the early 90s. And in contrast to fault attacks, this is a pure cryptanalytic attack. What this means is that we do not cheat at all by trying to manipulate the execution of the cipher, but we only use the interface of the block cipher to trigger this difference. So what we do is we encrypt two messages which are not exactly the same, like in fault attacks, but which have a difference between them. And then we also compute forward. We receive two different ciphertexts, and we also look at the difference between these two ciphertexts. And from knowing this difference, we try to learn something about the key, because the difference we observe tells us something about what happened to the message difference during the block cipher. Now, in case of fault attacks, we do something similar, except that we don't introduce the difference between the computations via the inputs. Instead, we do it by manipulating the computation. But then we use a similar method as before. We use the predicted intermediate result and compare it with what we observe to learn something about the key. So if we look specifically at the block cipher we saw before, this was a block cipher which had a 4-bit SBox. So a lookup table from 4 bits to 4 bits. So it has a total of 16 possible input values X. And here is the lookup table with the corresponding output values. And what we are now interested in is, what if we look at two inputs which have a specific input difference? In the example before, we said that we would fault the first bit position. This corresponds, if we write it down in hexadecimal, this corresponds to a difference of 8. So if the one input value was 0, 0, 0, or 0 in total, then the output value would be 1, 0, 0, or 8 in hexadecimal. So let's do this for all possible input combinations with this input difference and look at what the output difference looks like. So the first pair that we have is, if the one value is 0, then the corresponding input value with the difference of 8 is 8. These two values are mapped to the outputs of 2 and 1. If we take the XOR of these two, we get 3. So this means that one possibility, if the input difference value is 8, is that the output difference at the SBox is 3. Let's have a look at the next value combination, which is 1 and 9. Here we get the outputs 0 and D, which have a difference of D. Okay, that's something different than before. Let's go on. We again, if we take 2 and A, we again receive a different output difference. But if we look through all of the values, we notice that in total we only see 4 different output values if we use the same input difference. This means that there are several combinations of input values that lead to the same output difference. And if we know the input values exactly, we also know the output difference. But this also works the other way around. If we know that a particular input difference caused a particular output difference, this tells us something about the value that must have been mapped. Because, for example, if we take this output difference of 3, we can remember that one of the possible explanations for this was that the 2 input values were 0 and 8. Or they can also have been reversed. They could have been 8 and 0. And there are 2 other possible values that achieve this. So if we know exactly what input and output difference happened, we learn something about the value. We learn a set of possible solutions that maps this input difference to the output difference. And we can actually map this behavior in a table. So this is called the differential distribution table. And what we see here is that the rows here on the left-hand side, they are labeled with the input values, input differences of 0 to f. And the columns are labeled with the output difference also going from 0 to f. And each entry of the table tells us how many values with a particular input difference map to a particular output difference. So if we look at the column with the red numbers in the middle, this corresponds to what we saw on the previous slide. So if the input difference is 8, then we see that there are 4 different output differences, and all of them appear equally often. So they have the same probability of happening. This is 3, A, C, and D. And this tells us something also about the example with the differential fault analysis we saw before. Namely, if we introduce this sort of fault, then we already know that at the output difference of the S box, there must be exactly one of these 4 differences, 3, A, C, and D. And for each key guess, we receive some potential input and output values for the S box. And since all of these output values are equally likely, actually when we compute backwards, we receive for 1 out of 4 keys the correct input difference. So not only for the correct key, but also for 3 incorrect key guesses. And this is the reason why if we do this only once, we will end up having several remaining key candidates. And for this reason, we need to repeat the attack until we have narrowed down the list of key candidates. And we usually also repeat it some more times with different fault positions so that we can learn the entire key. Except if we are very, very careful and clever in positioning our fault, in which case we can learn very large parts of the key or even the complete key with just one fault. I think you heard such an example in the previous talk. Okay, but enough of this detour, but keep this sort of table in mind because we will see something similar later on. Okay, so let's return to fault attacks and let's have a look at fault attacks for a specific cipher, namely the Advanced Encryption Standard AES. I think you've already seen this design in the previous talk, so I will only summarize quickly what it looks like. It has, in the AES 128 version, a total of 10 rounds, which execute the following 4 operations. We first have an S box that maps each of the 4 by 4 byte matrix that is initialized in the beginning to the plaintext to a corresponding output byte based on lookup table. We have a shift row step, which moves around the individual bytes of the state. So this is a linear operation. We have another linear operation, which is called mixed columns, which works on the entire column at once. And the main purpose of this step is if there is a difference in one of these 4 bytes of an input column, we are guaranteed that all of the 4 bytes at the output are going to have a different as well. So this is the special property of the matrix that is used to compute this linear operation, namely an MDS matrix. And this is also very important for fault attacks. And finally, we have a key addition operation where in order to make the computation dependent on the key, we XOR the current round key to the state. So this round key is derived in some way from the master key, but we don't really care about the details how this works. In any case, these operations are repeated a total of 10 times in case of AES 128, except that we also have an additional key addition in the beginning, and the last round is a bit different because the mixed column step is missing. Okay, so let's recall two approaches of how we can attack the cipher with the help of fault attacks. And this is going to be in preparation for demonstrating the other types of fault attacks that I want to introduce. One very simple approach that is similar to the toy example we saw earlier is to again try to introduce a single bit flip in the last round, namely right before the S-box operation. So I've drawn here on the bottom the last two rounds of the AES. One such square always represents one AES state, and I've labeled here the operations SB for sub-bytes, so that's the S-box step. Then we have SR for shift rows, so shifting around the cells, and MC for mix columns. And so the last round starts right before the middle, the key addition drawn here in the middle. And if I introduce a fault, just like before, this will influence the S-box output. This will be then shifted by shift rows to no other position. It will stay in place. And finally, the key is going to be added. So if I introduce a fault here and I collect my two ciphertexts, the correct one and the faulty one, and I guess exactly one byte of the key byte marked in green here, which has a total of 2 to the 8 different potential values. Then using this key guess and the pair of values at the first output cell, I can compute backwards and check whether I observe exactly the 1-bit flip that I caused for this particular key candidate. If yes, I can keep it. If no, then the key candidate was wrong, assuming that my fault setup is very precise. And it can be clever to do this fault a bit earlier, because then the distinguishing property will depend not just on one byte of the key, but on more bytes. This makes it a bit more expensive to test all the key candidates. But the good thing is that I can also then learn a larger part of the key. Because if I do it just like I illustrated here, I will only learn one key byte from my fault. Whereas if I do it one round earlier, I can learn a total of 4 key bytes. So this is a cleverer way of doing things. So in this case, I would have to test a total of 2 to the 32 key guesses to compute backwards far enough because of the mixed column step in round 9. But the good thing is that I will then also learn all the 32 key bits. And what's also nice about this attack, if I do it earlier, is that it also works if I don't exactly do one bit flip, but I simply cause some sort of error in one byte. It doesn't have to have a specific difference, just some error. And if I do it this way, then I can optimize this attack so far that doing only 1 or 2 faulty encryptions allows me to recover the full key. But we don't care about these optimizations too much, because in the rest of the talk, we are going to need a lot more than just 2 faulty encryptions. But the good thing is going to be it's going to work even when our fault introduction method is very, very imprecise and doesn't always work. So let's have a look at classical countermeasures against these attacks. So how do we prevent this type of differential fault attacks? I can do this sort of countermeasures on different levels. So one approach is that I take the physical circuit and try to optimize this in a way that it's harder for the attacker to introduce a fault. For example, I can shield the circuit. I can make it harder for the attacker to get to the actual circuit, for example, for shooting at it with a laser or for tampering with the wires. I can also try to detect whenever an attacker tries something like this. So for example, I could have some light sensors on my circuit which detect when the attacker tries to remove the cover and the packaging of the circuit to get to the actual circuit and tamper with it. So this is on a physical level. What this usually does is it makes it harder, but usually not impossible for an attacker, but the cost of doing something increases a lot. On the other hand, since this doesn't have an immediate impact on how the attacks work, I'm going to ignore this type of countermeasures in the following. What I'm instead more interested in is implementation level countermeasures. And the most popular in this category are trying to detect whenever an error happened in the computation. For example, by executing each computation 2 times and comparing the outputs whether they match. This can go even further. I can even try to correct errors. For example, what I can do is I can execute my circuit not just 2 times, but 3 times. And whenever I notice that not all 3 are the same, I do a sort of majority voting. So if 2 are the same and 1 is different, then I can assume that the different one is the faulty one, and the 2 that are the same are probably the correct ones. And I will use this as the cipher output. What I can also do is I can again make it more expensive for an attacker to cause the right sort of fault. And I can do this by randomizing the details of how I execute the cipher. For example, I can shuffle around the order of the operations that I do. Or I can try to insert a lot of dummy operations that don't really do anything, but that appear at random positions, in different positions every time, which will make it a lot harder for the attacker to hit the right position. There is a third level where I can introduce countermeasures, and that is on the protocol level. So this is not inside the implementation of the cipher, but in the surrounding protocol where the cipher is used. So I can try to keep to prevent an attacker from actually collecting any useful data. I can do this, for example, by allowing my cipher implementation or my protocol run by allowing the block cipher to only be executed a very limited number of times per key. For example, by updating the key after every use. Or what I can also do is I can try to randomize the inputs that I work on in some way. So let's have a look at some of these which are relevant for the stock in some more detail. And I'm going to look now at 3 different countermeasures which also all try to prevent the same sort of property that differential fault attacks need. Namely, we saw before, to do a differential fault attack, the attacker needed access to the faulty ciphertext, so to the output of the computation where the fault was inserted, and to the correct ciphertext, so to another computation on the same input where the error did not happen. And this is actually a very strong requirement that I can try to keep an attacker from achieving. And one way to do this is the error detection that I already mentioned. So whenever I want to encrypt a plain text M, I encrypt it not just once, but twice. And I compare the 2 outputs of these computations. And I only accept the computation if the outputs match, in which case I guess that none of the 2 was attacked, and then I return the result. So if I do this, it will be much harder for the attacker to achieve or to get a faulty ciphertext at all, assuming, as we usually do, that the attacker is not able to introduce more than one precise fault in exactly the same way in two computations. So if I look at this, for example, in hardware, and I assume that the two block cipher calls for this countermeasure are implemented side by side, then the assumption is usually that it's very hard for the attacker to cause exactly the same error in both executions. And this is what I would need to do in order to get this faulty ciphertext, because if I do the same error in both executions, then I get the same two faulty outputs, and will actually, the detection will not notice that something happened and will give me this output. So this makes it a lot harder for the attacker to collect the necessary data. Okay, so this is an implementation level countermeasure. It's in the way how I implement the circuit. There is actually, in many cases where block ciphers are used, a sort of natural countermeasure against this type of attack. Namely, whenever I use this block cipher as a part of an authenticated encryption scheme, or short AEAD. What's an authenticated encryption scheme? It's a particular use of block ciphers to encrypt data so that it's not only confidential, meaning no one can read it based on the ciphertext, but authenticated encryption also protects integrity, meaning it appends a short tag or checksum at the end of the ciphertext, and only if this tag is correct in the decryption, so if this is verified successfully, the plaintext is returned. So it makes sure that the received message is authentic and was not changed during transit. And this is actually how block ciphers are used most often. So when you look at a protocol like TLS or SSH or all kinds of communication protocols, they usually do authenticated encryption inside. For example, they use a mode of operation like AES-GCM or AES-CCM. And the thing is that if we use this, then there's a sort of natural protection against false attacks. Because what this authenticated encryption also does is it randomizes each encryption. So whenever I encrypt a message, I also generate a random or unique value called the nonce. And this will never be the same two times. When the attacker tries to encrypt the same message twice, this will not happen with the same nonce. And this will also mean that the block cipher inputs are going to be different because they are going to depend on the nonce and the message. So what this means is that this makes it impossible for the attacker to get both the correct and the faulty ciphertext for the same message, because I can only encrypt the same message with the same randomizer once. It's also important here to look not just at the encryption procedure, but also at decryption, because the decryption actually does accept the same nonce multiple times. However, it only returns the resulting plaintext when the authentication tag was checked successfully. So if we cause some sort of fault during the computation, then for most authenticated encryption ciphers, there will also be an error detected during the tag verification, in which case we don't get the faulty computation output back. So for most authenticated encryption schemes, if they are implemented properly, we actually have a natural protection against fault attacks. We will have a look at how to get around this in a moment. I want to mention a third countermeasure that is a bit more effective than detection in many cases. It looks a bit similar at first glance, but it's called infection because it does not just the two computations, so two redundant computations to check those for equality. It additionally does many dummy operations. So it executes, for example, if the block cipher is AES, it executes not just two AES calls, but also many dummy AES rounds. And what this countermeasure will do in the example instance that I cite here, it will check after every round if the two redundant computations still match, and it will also check whether the dummy operations were executed without an error. And this is because the dummy operations are executed on a special value, which will stay the same after each round. We don't care about the details here. But the thing is that whenever this countermeasure notices that either the two computations are no longer the same or my dummy computations produced an error, then it will always start overwriting the intermediate results of the regular computations with this garbage from the dummy operations. So this means that if an error happened, the attacker will not receive no output, like in the case of detection. Instead, it will receive garbage output, because if there was an error, it will get some dummy operations from the dummy rounds. And since these do not depend on the key at all, this garbage value is completely unusable for an attacker. And this makes it very hard for an attacker to distinguish between the cases whether a fault was successful or not. Okay, so these are now 3 countermeasures which prevent the standard sort of fault attack, but we will now get closer to seeing how we can get around these countermeasures. And for this, I want to mention 2 variants of fault attacks which our attack is based on. And the first of these is so-called
Sorry, Mario, can I ask a question?
Yeah, sure.
In the previous slide, to get rid of the random output, can we repeat the attack? Because if you don't have the fault in your state, or for example, C and C prime are the same, then the output will be the same always. But for the faulty one, you have a random value. And for the different, even if you repeat the same fault, you receive different values at the output. So to get rid of this beta value, which for the faulty ciphers, we can just repeat the attack. Am I right?
You can repeat the attack in order to detect whether your fault caused any error or not.
Yeah, exactly.
Yeah, that's what you can do. However, what's maybe relevant to notice here is that these dummy rounds, their position when they're executed, this is randomized. So I didn't mention this here, but this countermeasure also uses a random bit string. And this random bit string will tell it in each of the total number of rounds. So in total, for example, for AES, we would have 11 plus 11 rounds for the regular computations, plus some parameterizable number of dummy rounds. Right. And in which order these are executed will be randomized. So between 2 executions, if you do fault 2 of them, you will not receive the same dummy output both times. But if you do not fault it, then of course you will receive the correct output. So if you can run it multiple times, you can at least distinguish whether you got the correct output or not. So this works.
Thank you.
Okay. I see there were some questions in the chat, but I missed those. Is there anything that I should still answer at this point?
I think you will going to answer their question, because there was a question whether the attack model is on the protocol model level or on the primitive level, which I think SIFA is going to be on the primitive level, but I think you will explain later.
Yes, I will explain that later. Yeah. Okay, so let's have a look at these fault attack variants that I mentioned. So the first of these is ineffective fault attacks, proposed by Clavier et al. And these are attacks that work when the error we cause is not something like a bit flip, but an error that produces some reliable value. For example, it can be a stuck at error that always replaces an intermediate result by 0, whatever it was before. And if an attacker can do such very reliable errors with a known result, then there are actually also very easy attacks possible, which are not exactly differential fault attacks, but something different. So in the case of AES, this is actually super simple. So if I have a fault setup where I can set, for example, an entire byte to 0, then something very, very easy that I can do is I can set 1 byte in the last round right before the key addition to 0. The key is going to be added which means the first byte of the output is going to be exactly the value of the last round key. So this is, of course, super simple. And I can also make it a bit more powerful if I do this attack or do this fault at an earlier step, because in that case, I also know the value of some intermediate variable, and I can again do key guessing like before, compute backwards and check for this value. And in particular, what's so nice about this type of fault is that this fault is not actually always effective, in the sense that it doesn't actually always change the computation. Because what happens if the value at this position was already 0 before I applied the fault? In this case, the fault didn't actually change anything. So in particular, if I have some infection or error correction countermeasure, this fault will not be detected because it didn't do anything, which means the attacker would actually receive the output of this computation even if they faulted an intermediate value. And what they will know from this is, okay, this was a ciphertext or a message where this intermediate variable was already 0. So again, even if they receive only the output where nothing actually happened from the fault, they will know this intermediate value and can again compute backwards and check whether there is a 0 at this position. So this is an attack that can work even if you have a detection countermeasure in place, because it works if I only use the unchanged cipher computations and not those where something actually changed. There is another very important attack that ours is also based on, and that is statistical fault attacks. These again work under the assumption that the error that we cause isn't a bit flip, but some sort of biased error. This can be now a bit more vague than in the previous attack. For example, it can be something that happens only sometimes. It can be a fault that sometimes resets a value to 0 and sometimes it doesn't. And then I can use a very similar fault setup as before, where I attack around number 9, like you already saw on the previous slide. But instead of checking for a specific difference here, what I can do is I can check for the distribution at this point, because the assumption here is the following. The assumption is that the fault has some effect, like for example, setting one of the bits to 0 in many cases. We don't know which bit position exactly, and we don't know how often, but the end result is going to be that the values with more zeros are going to appear more frequently at this position, because that's what the fault does. It biases the distribution. And what we can now do is, what you can now do to verify whether a key candidate is correct is, we can again compute backwards, not just for one value, but for many values, and collect all the values that we get at this faulted position. And then we check whether this looks like a uniform distribution, like it should in a normal cipher run, or whether this looks like a non-uniform, biased distribution, because our fault caused a bias. And to do this, I need many faulted output values, because I want to say something about the statistics, the distribution of the values, and not just one specific value. And then I can actually verify this non-uniformity by one of several available tests. So two of the most widely used ones are the squared Euclidean imbalance, or SEI, or a closely related metric, the chi-squared coefficient, Pearson's chi-squared coefficient. What both of these do is they try to compute the distance between a distribution that I observed and a uniform distribution. And then I want to do a statistical test whether what I observe looks more like the bias distribution or more like the uniform distribution. And this SEI test or chi-squared test is going to give me an answer that. So is it more likely that this is uniform or more likely that this is biased? Of course, if I have a lot of data, this will be very easy to answer. If I have not so much data, then there's going to be a higher variance in the result, and the result may not be so clear. And what our proposed attack does is it combines some ideas from this one here, namely having a bias distribution and testing the non-uniformity of this distribution on the one hand, and on the other hand, on taking only executions where no error actually happened. We want to combine these two. And if we do this, then we also can circumvent one more countermeasure that I want to mention next, namely countermeasures that have nothing to do with fault attacks at all, but with side channel attacks. And the thing is that in real implementations, if they are protected against one of these two types of implementation attacks, they're usually also protected against the other. And while differential fault attacks don't care so much about these side channel countermeasures, the effectiveness of these two attacks, and in particular of the ineffective fault attack, is very sensitive to this. So this was nice because it defeated error detection, but it does not defeat these side channel countermeasures. Because what this ineffective fault attacks did in some ways, it allowed us to peek at one of the intermediate variables and learn its value. And this is exactly what side channel attacks also try to do. They try to learn one of the intermediate values. And there are already many countermeasures against this, which try to make it more difficult for the attacker to observe the same value repeatedly, for example, by randomizing the order of instructions or inserting dummy instructions. And they also try to make sure that even if the adversary or the attacker learns some intermediate values of the circuit, this won't be useful. And the most important type of countermeasure of this sort is masking. What masking does is it takes one intermediate, so for each intermediate bit in my SIFA computation, it replaces it by a number of random bits, where so we have a total of d plus 1 random bits. D of them are completely random, and the last bit is chosen in such a way that the sum, the XOR sum of all these bits xi results exactly in the original value. So it splits the original value into several shares, and only if I know all the shares, I can know the real value. If at least one of the shares is missing, the value is going to be completely uniformly distributed, and I can draw no link to the original value at this point. And for all these attacks, I always need the original value because this is what depends on the key. So if I have a masked implementation, this is going to be a lot bigger than a regular implementation. I think you're going to hear more details about it in the next days. And you maybe also heard about it in the preparatory sessions, I don't know. In any case, the circuit is going to grow a lot bigger because there are more bits involved. And if I learn only these intermediate bits, this is going to be absolutely useless in learning anything about the key. So this helps against side channel attacks, but also against ineffective fault attacks. So let's now see how we can get around this by combining the two last fault attacks that we saw. Statistical attacks, which looked at the distribution in a value, and ineffective attacks, which looked only at the SIFA outputs where the fault had no effect, didn't change anything. And the underlying idea for this attack is actually twofold. So we're going to change two things compared to what we've done so far. So far, we've always inserted the fault, so shot with our laser or so, right before or right after the S boxes, usually right before them. And we also always assumed and still assume that the attacker can only place one fault. And we saw already that for the attacks we saw so far, either error detection or masking always prevented these attacks. And we're now going to change two things. The first thing is that we're only going to use those faulty encryptions where no fault was actually detected at the output. This means that these are those cases where we did successfully shoot with a laser or something. However, whatever this fault did, whatever effect it caused, this effect did not change the intermediate variables, meaning it didn't change anything about the computations. Like, for example, we set something to 0, but it was already 0 beforehand, so the fault didn't change anything. And we're going to hope that this leads to a bias in some intermediate variables, using only the specific faults. And I first want to talk primarily about this idea because it was what we did in the original SIFA paper. So SIFA is short for Statistical Ineffective Fault Attacks. However, there's also a second idea, which I want to have a look at afterwards. And this idea is to do the fault not right before the S-box where we also measure, but we're going to place the fault inside the S-box circuit. These are intermediate values that we can't use during the key recovery attack. So we're going to measure the effect either before or after the S-box. So the place where we put the fault is no longer going to be the same where we measure the effect of the fault. And the good thing is, if we do both of these things, we can defeat protected implementations which have both masking and error detection in place. However, there is also a downside. Our attack usually requires a lot of messages, so a lot of repeated executions of the same fault. For example, we can do this by putting a permanent damage in the circuit, like, for example, cutting a wire or so, and then always run this encryption with fresh messages. So we don't need 1,000 encryptions of the same message. We just need that the cipher is executed with the same key many times, and it always shows or often shows the same fault. It doesn't always have to be the case, but at least reasonably often. Okay, so let's have a look at the first idea, keeping only faulty encryptions where no fault was detected. And to see when this happens, we're going to have a look at something called fault distribution tables. So the question here is, if we look at a certain type of fault effect, like a bit flip or a stuck at 0 fault, under which conditions is it ineffective, and what does the output of this look like? So we're only going to consider the cases where the faulted value x with the lightning bolt is the same as the unfaulted correct value x. So here on the left-hand side, you see such a fault distribution table for an example of a 2-bit value. So we have an original value which is either 00 or 01 or 10 or 11. And we are going to apply our fault, which in this case is stuck at 0. So all bits will be set to 0. And then we look at the faulted output. What you can see in the table here is these entries 1, 0, 0, 0 means with what probability is the value listed in the column here being the result if we apply the fault to the value given in the row. So for example, if the value was originally 0, 1, so the second line, then the output is of course going to be 0, 0, just like in all other cases. So what we are now interested in are those cases where the fault did not change anything. And this is exactly on the diagonal of our fault distribution table, because on the diagonal, the value in the row, which is the original input, is the same as the value in the column, which is the faulted value. And then we want to have a look at what the distribution on this diagonal looks like. In this first case, this is very, very simple. Since the output is always changed to 0, 0, the fault can only be ineffective if it was already 0, 0. So if we take only the samples where the fault had no effect, what we're going to end up with is 100% 0, 0 values. And this is what you see at the bottom here. So the red line marks what the uniform distribution would be. So each value would be equally likely, whereas the bar shows what happens if we look at only the ineffective faults. And this is clearly a biased distribution. Now let's have a look at another case where we don't always stuck at 0, but where each bit only flips to 0 with a certain probability, for example, 50% in this case. This is something that happens, for example, if you look at row hammer attacks. There, ones flip to zeros with a certain probability because the fault execution doesn't always work. Here we can see that if it was already 0, it will definitely stay so. But if it had some ones in it, then with a certain probability, we will switch to a value with more zeros. If we look at the diagonal now, we see more different values here. We also notice that they don't actually sum up to 1, but that's fine because we need to weigh each value with the probability of each input of occurring. So if we look at this distribution now, we still see that if we take only the ineffective fault cases, most often this is going to be because the original value was 0, 0, but it can also be one of the other cases. So we can't definitely say what the original value was in this case of ineffective fault, but we do see a bias. What this means is we can't directly use an ineffective fault attack, but we could use this statistical approach here. There are also cases where this approach is not really useful. For example, in a bit flip, actually, since every bit is definitely changed, there aren't going to be any cases where the fault is ineffective. There's always a change, meaning we don't get any usable distribution because we don't get any cases at all. So what we're interested in is faults like the first two, where the ineffective cases have a non-uniform distribution. And if this is the case, then we can do the following attack. We can inject our fault in a particular position. This is going to cause this non-uniform ineffective distribution, which we are now going to call P. So this is the distribution. How likely is each value X under the condition that the fault didn't change anything? And we assume that we are attacking an implementation with some sort of error detection, meaning as an attacker, we will only receive the outputs if no error was detected. So exactly in these ineffective cases. This means we will only get the output for a certain percentage of the samples we do. So we call this the fault ineffectivity rate. And this is the probability that a fault does nothing in one of our samples. So if we do n runs, we are going to only receive pi times n of the outputs. And now we have a collection of samples in which this intermediate value x bold has a bias distribution. So now we can apply the methods like we did in statistical fault attacks, meaning we guess the key for many of the samples we have, compute backwards, and check whether the distribution is non-uniform. We can either use this chi-squared or SEI metric that I mentioned before, or if we actually know what the distribution should look like, the ineffective distribution, we can do even more effective tests like the log likelihood ratio or LLR. And whatever test we use, it's going to tell us, is this more likely uniform or is this non-uniform? If it's uniform, then the key was probably incorrect. If it looks non-uniform, the key was probably correct because we observe the bias that we expect. And the nice thing is that this approach also works if the fault induction method, so for example, our laser or our row hammer, is noisy, meaning it works only sometimes with a certain probability or signal sigma. In the other case is something, nothing happens or a random garbage happens or whatever. So this is nice in realistic scenarios where I don't have a very expensive setup. So let's have a look briefly at an example. Let's look again at this random AND fault, so where each bit flips to 0 with a certain probability, and this for a full byte. So if we shoot 1 byte, then each of the bits of these bytes is going to flip to 0 with a certain probability of 1/2. What this means about our fault ineffectivity rate is the following. So when is this fault ineffective? It's ineffective if either the value was already 0, then it certainly doesn't do anything for each bit, or if the bit was 1 and did not flip. because it only sometimes flips. So in total, per bit, we have a probability of 3 divided by 4 that nothing changes. And the probability that nothing changes for any of the bits of the byte is this value to the power of 8. In total, that's about 10%. So if we have this sort of fault, then about 1 in every 10 fault inductions will be ineffective. And now let's assume that what we're targeting is an AES implementation with this infection countermeasure that I mentioned before, where we have these dummy rounds. And I'm going to assume that we have as many dummy rounds as we have regular rounds. Then you can compute what the best round to target is as an attacker. And with a certain probability, we then hit the round we were aiming for example, round 9. In the other cases, we either hit a dummy round or we hit one of the wrong ones of our SIFA computation. And in total, in about 1 of 3 cases, we achieve the fault that we want. In the other cases, nothing happens or garbage happens. What does this mean for the ineffective distribution if we take only the ineffective samples? It means that it will be a mix of this bias distribution, which has more zeros than ones. This is sigma times some probability. And in the other cases, 1 minus sigma, we're going to have a uniform distribution. This is if random garbage happens. And below you see a picture of these distributions. So the dark line is the uniform distribution that we expect for a wrong key. And the blue bars are the biased distribution that we expect for the correct key. We see that the cases with more zeros appear more frequently here, because these are ineffective with a higher probability. And if I now implement this attack on the cipher, so here we have some numbers from a simulation. On the left-hand side for the case where we know the correct distribution, where we can use the LLR metric, and on the right-hand side for the other case. And what we can see here is we have this reddish area on the bottom. The dashed line indicates the expected behavior. So this is the expected metric we would receive for the best of all the wrong keys. And the darker line and the corresponding dashed line is the prediction and the actual results for the correct key. And we see that after a certain number of iterations, about 400 in this case, is the prediction, the right key is going to clearly stand out above all the wrong keys. And from this point on, so a bit after this intersection, we can reliably distinguish the correct key. So this means we need about 400 samples, ineffective samples, to measure this. In the cases of LLR, in the case of the chi-squared statistic, we need a bit more, so more than 1,000, because here we assume a bit less knowledge than the other case. And these predictions are based on a statistical model that we describe in more detail in the paper. Essentially, it describes the distribution of the correct and the wrong keys in terms of some normal distributions, and then makes some predictions which are very similar to what we do in differential cryptanalysis in order to distinguish these two cases. So in the paper, we also have some real measurements, but I included these simulation results here because in the simulation, we have a better understanding of what our fault model is. So only here we can actually use this LLR statistic. In the practical results we didn't have such a precise model of what the fault actually does. It was some clock glitching, and we simply looked at the output without knowing exactly what the fault actually did. Okay, so let's now have a look at the second idea that makes SIFA interesting. So the first one allows us to get around detection countermeasures, essentially, because it works only with the cases where the fault is not detected. And now we need another idea. So far we always placed our fault before or after the S box and also measured there. And the following, we're going to place the fault somewhere inside the S box computation. So we're going to look at implementations where the S box is implemented as a circuit, like it most often is in hardware. And we're going to fault one of these operations in the S box circuit. And then we're going to statistically evaluate not exactly this intermediate position, but the output of the S box. And the nice thing about this is if we do it, then we can actually also work not only with biased faults, but also with bit flip faults, because bit flip faults somewhere in the middle can actually cause a nice non-uniform distribution in the output. And the second thing is that this is going to work even for masked implementations, where we fault only a masked value. And the trick is going to be that, so the implementations we look at now are doubly protected, right? They have a detection countermeasure, meaning we execute our cipher multiple times. This is illustrated here with these large sheets, and compare their output results to see whether they match. And the second countermeasure is this masking, meaning each intermediate bit is split into several intermediate bits which are randomized, so that only their sum is actually related to the key that is processed. And regularly in the implementation, we only ever get to see these randomized shares, whereas with our attack, we can actually learn something about the original value, even though this original value never actually appears in the circuit, but we still learn something about it. And to look at this, we actually need to look inside a cipher. So I needed to take a smaller S box at this point. And I selected the S box of the cipher SHA-3, or of the hash function SHA-3, because it's already pretty small, and I made it even smaller. So it's now just a 3-bit S box, so that it fits on the slides. And it's going to be masked using 2 shares. So each of the 3 input bits is going to be written as the sum of 2 shares. And the output is also going to be a masked version. So each output bit, RST, is also going to be the XOR of 2 shares. And the circuit we have here uses 3 kinds of gates: XOR gates, AND gates, and NOT gates. If you're an electrical engineer, you might be a bit wondering about the notation I use here. This is more the cryptanalyst or algebraic notation that I'm using here. So what does the circuit look like? We have these 6 input shares, A, B, C, and 6 output shares. And in between, we have a number of AND gates. So in some cases, one of the inputs goes through a NOT before, and we have some XORs. And the fault I'm going to place is going sometime during execution in the algorithm. And at this point, I'm going to fault the value of A0. This is marked with the lightning bolt here. So the point in time when I introduce my fault. And from that point onwards, this variable is going to be faulty because I flipped it at that point, and it's afterwards going to be fed into several AND gates. Now the big question is, under which conditions does this fault not have an effect in the output? I'm assuming I'm flipping the bit here. So the question is, when is this ineffective? This depends on the other inputs of the AND gates that I'm propagating to. Because in an AND gate, if one of the 2 inputs is 0, the output is definitely going to be 0, no matter what the other input was. So if my other input was 0, then flipping the 1 input bit I faulted doesn't make a difference for the output. So this means that the output is ineffective in the following cases. So let's first look at the very right. At the very right, we see that the faulty red value is combined with the value C1. So if C1 is 0, then the output of the AND gate will remain unchanged. If we now look at the left, here we see that the 2 red faulty values are combined first with B0 and second with B1. And also the outputs of these AND gates are going to be XORed afterwards. Now, when is this XORed result unchanged? It's unchanged if either both AND gates flip their output, because then it will cancel out, or if none of the AND gates flip their output. So in other words, the fault is ineffective if first C1 is 0, and second, either both B0 and B1 are 0, or both P0 and P1 are 1. In both of these cases, the original value B must have been exactly the same, because B, the original input value bit, the unshared bit, is the XOR of the two. And no matter which of the two cases, this is always 0, which means if we see that the output value of this S box was unchanged, then we learn that one of the unshared input bits must have been 0. So in other words, the 3-bit S box input had a bias. Values where B equals 0 are those that are occurring more often. And we now can use this 1-bit information like before to recover the key. So if we execute this in practice, in the paper we did this, for example, so my colleague Robert did this for the example of AES. Then in the case of a correct key guess, we will have some, so we see here in AES state, we will see a very non-uniform distribution here with the white background, whereas in all the wrong key guesses, we will see mostly noise, or noise in all cells. So to summarize, we took some ideas from differential cryptanalysis, which we can normally protect the SIFA against by just using better cryptography. But if we cheat with differential fault attacks, then we can still use very similar methods. We can defend against differential fault attacks with things like noise or detection countermeasures or authenticated encryption. But in that case, we could switch to statistical fault attacks, even in the presence of noise, and even also in the presence of authenticated encryption, like we show in another paper. We can defend against statistical fault attacks still with detection countermeasures. We did see a previous fault attack that works even for detection, and that is ineffective fault attacks, but we can defeat those by applying masking. And our attacks, statistically ineffective fault attacks, work even if we do all of the previous countermeasures. So even if we have good crypto, noisy samples, authenticated encryption, detection and masking, it still works. So finally, a few words about how to protect against this powerful attack. One of the reasons why this worked on the masked implementation, despite the masking, is the following. So masking always relies on the fact that each single gate in the circuit is a so-called incomplete operation, which means learning all of its inputs of one gate doesn't tell us anything about the original variables, because there's from each variable one share is going to be missing. So even if we learn all the gate inputs, we will never learn all shares of one variable. But what SIFA did is it placed a fault that can propagate to several nonlinear gates, in the previous example to 3. And whether it becomes ineffective or not depends on all inputs of all of these AND gates. In other words, we learn something about the inputs from multiple gates. And this is the big trick, because this may include all shares of one variable. In the previous example, all shares of B. So how can we protect against this? We need to prevent exactly this situation. So we call an implementation single fault SIFA resistant if each possible single fault that we could place is either detected by the error detection, so it's not ineffective and we don't use it because we don't get it, or it activates at most one nonlinear gate. The second condition was violated in the previous one because we saw there were some faults which could propagate to multiple nonlinear gates. And this is what we absolutely need to avoid. We need to make sure that every variable that goes to multiple nonlinear gates must also activate the error detector. And this is the big idea behind our countermeasure. And for this, we need to adapt the error detection circuit to make sure it detects all errors that could influence at least two nonlinear gates. And we propose two ways of doing this. The first one is with adding local checks. So locally, whenever there is a critical fault position that could influence multiple gates, like the one we saw before, then we add an error check at this point, which means at this point, we compare the value to the second redundant computation that we do. And how we do this is we describe in the paper how we can analyze the circuit to identify all these critical positions that could propagate to multiple nonlinear gates, so to multiple AND gates. And this can be done relatively generically for any sort of S-box. So for example, for AES or Ketchuk or any sort of S-box. However, if we do this directly, it may lead to many required checks because we just identify the places where we need checks. We can also try to do something more elegant, namely global checks. We can try to make sure that all of these critical positions somehow influence the final result of the computation, so that an error in this place is guaranteed to propagate to the output. And this usually means not just adding checks to the circuit, but rewriting the circuit, shaping it into a different way. And this doesn't always work, and it can be very hard to manipulate the circuit this way. But we do propose an approach in our paper suggested by Christoph, which works quite well for quite a number of particularly small S-boxes. And that is to rewrite the original S-box using only a specific kind of invertible gates, which can be computed both forward and backward. And in the paper specifically, we look at the Toffoli gates, which is a gate that adds the AND of 2 bits to the third bit. And all 3 bits are then go on to the output. And if we can rewrite our circuit this way, then all bits that could go into the AND gate also propagate to the output and will thus influence the output. So if we can manage to rewrite our circuit this way, then we can get away with a global check, meaning we only check the final output of the cipher, like in the traditional error detection mechanisms. So here I have these 2 methods applied to the circuit we saw before. So this is the case with local checks. We saw before that these vertical lines that go down from ABC, they all go into multiple AND gates. So these are definitely critical values that we must check after they went into all of the AND gates. So we add 6 checks here at these positions, marked in green. What I also added here on the right-hand side and bottom is the resharing that is necessary to keep the masking valid. We don't care about the details of that here. So this is the variant with local checks. This means at these 6-bit positions, I need to check up with my second evaluation of the cipher and compare if each of these bits is still correct. And if there is an error, I abort the computation and return nothing or garbage or whatever. And now the case of the global checks, you will notice that I haven't added any checkboxes here. What I've done instead is that I've reorganized the circuit in such a way that each of the values ABC, 0 and 1, is XORed at the end to one of the other intermediate output results. So whenever something flips in one of these lines here, it will definitely go into this XOR, and since XOR simply forwards every error, this will also definitely cause an error or a bit flip in the output of the S-box. And then furthermore, it would also more specifically cause actually an error in each unshared variable, and then it's guaranteed to also show up in the cipher output. Now this circuit here was just restructured by hand with a lot of trial and error, but in the paper we also proposed this more organized approach that uses Toffoli gates. But this definitely wouldn't fit on the slide anymore. Okay, so let's conclude what I talked about. I tried to convince you that statistically ineffective fault attacks are a very powerful type of fault attacks because they're effective against the countermeasures that we typically see in state-of-the-art protected implementations, in particular against both error detection or infection, and side channel countermeasures like hiding and masking. Hiding because it works even when we have only noisy information, because we have a statistical approach. Noise just means we need a bit more samples. And on the other hand, it also works with masking because we saw that if we do the fault inside the S box, it can propagate to multiple places and we learn values at multiple places, which masking doesn't protect against. We proposed this new countermeasure in 2020. The first author listed here in the alphabetical author list, by the way, is Johan Dahmen, who I think you're going to hear from in a talk in one of the next days. And this combines masking and detection with a special circuit structure. So we make sure that the circuit has this special structure that all faults that could trigger more than one AND gate are detected either with local checks or at the very end in case of this global check approach. And we've also seen the publication of several other methods to protect against this attack. Now, they vary very much in their effectivity. So some work against this masking attack on mask implementations and some don't. And their efficiency is also very different. So some of these examples are based, for example, on error correction mechanisms instead of error detection. And in all of these cases, it's usually a fact that with enough effort, money, time, and data, an attacker can still be able to defeat your countermeasures in some way. So even if with our newer countermeasures, we only protect up to a certain number of faults. I've explained here only the single fault one. In the paper, we also describe what to do with multiple faults. But the countermeasures then very soon become very expensive. So optimizing this, by the way, would be a highly relevant open research topic if you're interested in this. What in the end we are always trying to achieve is that the effort for the attacker to circumvent our countermeasures is higher than it's worth for the attacker. That's essentially the combined idea of all of this. So with this, I'd like to thank you for your attention, even though I took a few minutes longer with the mic problems in the beginning. And I hope you have some questions for me.
Thank you very much, Maria, for the nice presentation. Very amazing. I think audiences have some questions. The first question comes from Sina. Sina, your microphone is...
Hi, can you hear me?
Yes, I can.
Hi, and thanks for the awesome presentation. I'm on the subject of the global checks that you mentioned that passing XORs, the errors pass the XOR, but can't we just use faults that cause an error on both inputs of the XOR and thus kind of bypassing this global check?
You mean in this picture here?
Yeah, if we make some faults that both inputs of the XOR are inverted, then the inversion doesn't pass the XOR.
That's an excellent observation and question. That's absolutely correct. So if it would be possible to place a fault that triggers not just one, but both inputs, then the result would indeed disappear. However, we've taken care to structure this circuit in such a way that this cannot happen. So if you follow along where these two inputs of each XOR come from, you will notice that there is no single point which has a path to both inputs of the XOR. And this is what we would need in order to flip both, because we assume that we only have a single point for error introduction. So this is one of the graph-based properties that we also discuss in the paper, which I didn't go into detail here, but the specific example here is protected against this sort. But this is not easy to do in general. So this is one of the reasons why global checks are so difficult.
Thank you.
Thanks a lot for the great question.
Big question there. I also have a question, whether I think there is no gold solution against SIFA. Am I right? Because any solution can be bypassed by the case of by the sake of time and money. Am I right?
I agree that there is no complete solution because you can always try to, for example, invest in a more expensive fault setup so that you can, for example, do 2 faults instead of 1 and so on. So it always only works under a specific attacker model and fault model. And we've optimized specifically for the 1 fault model and only sketched a solution for multiple faults that is also going to be expensive relatively soon. So protecting against SIFA, against a strong SIFA adversary who can, for example, do multiple faults or who can do combined attacks like a fault and a side channel measurement, this becomes very, very expensive to build. And it's usually more expensive than we would like. So there is indeed no complete gold solution that I'm aware of that completely eliminates this attack against a well-funded adversary.
So it means that we cannot provide a provable solution against SIFA.
Well, provable, yes, but provable only for a specific fault model and not for all possible adversaries.
Yes, if we restrict
to the best of my knowledge
to a specific type of the fault, yes, then we can maybe
a
find
specific number of faults in specifically. Yeah. I mean, there are, of course, things like protocol level countermeasures like choosing a new key for every encryption. This will never allow an attacker to collect sufficiently many samples. So if this is something possible, if we have a higher level countermeasure that we can rely on, then this does work effectively. But this limits the applicability essentially because it has some strong requirements for the protocol that we are using. And it also assumes that the attacker can't put a fault in the protocol, for example, to skip the key update or something like that. So there is always some caveats, some limitation in which an attacker could still do something outside the attacker model and execute SIFA.
Yes, thank you for the clarification and answers. I think we reached the end time. Is there any question from the participant? Okay, Maria, I would like to thank you again for the nice presentation, and hopefully situation gets better and we can meet you in Iran to discuss things, and also you can visit Iran and nice cultural places of Iran, and students can meet you personally here.
Mm-hmm. Thanks for hosting me virtually, and I hope you enjoy the next days of the winter school.
Thank you very much. Any closing remarks?
No, not really, except have a great afternoon and enjoy the next talks.
You too. Thank you very much. So we can end up the meeting.
Bye.
Thank you. Bye.